In this lesson, we'll look at how to use log arrays to transform a given relationship to a linear form. We'll also look at the most important question of why we do this. I'd like you to pause the movie and read this question. I plotted for you the data, the number of hours, again P, thousands of bacteria. And this is how the graph looks like. So pause the movie and read the question. We collect and use data in order to make predictions. So the shape of our data looks like this. Might be a linear, or might be a quadratic, or might be an exponential. We don't know for sure. However, it is given here the shape of it, so we can see it is an exponential, r to the power of t. So unknown is to the power of t. However, it is very difficult to use this shape to make predictions. Also, when we have very big numbers, the graph will look distorted. If my next observation, for example, 4 or 14, is going to be here 100,000, the graph will look very distorted because I can't use clearly such a big number on the y-axis. That's why I very often use the technique of changing these relationships into linear ones. So let's see how we do it. I write the relationship. Now see, they use some different letters. In this case, t is my old x and p of t is the y. You can write it if you want, y equals k r to the power of x, if it's simpler for you. So don't forget that these are the notations. Now I want x to be brought down so that I transform this into a linear, which is easier to draw and use for prediction. And I know that if I apply log in both sides, I'm going to get this one. I can now transform it in order to get a linear function. So log y equals log k plus x log r. And see how this one will be the new y. I'm going to call it capital Y. The new x is the same as the old x. I'm going to call it capital X, but it's the same as the old x. This will be the y-intercept of the graph, and this will be the slope. So what I need to draw is y equals log k plus x log r. That's why the new x is the same as the old x. The new y, it's log old y. So in my calculator, I'm going to create a new column that I'm going to call log of y. And then I put it here, and I'm going to graph old x against new y. So here is what I get. I calculate in this column log of p. Yeah. So this was the old x. So old x, which is the same as the new x. And this one is the old y, and this one is the new y. So the new y comes on the y-axis, and the x stays the same. And see how now the equation is transformed into a linear equation. Why do people do this in practice? Because it's easier to estimate point on a line than on the curve that we had before. Also, being a line, I can make better prediction on what happened for bigger values than 12, so it's easier. Now to get the equation of this line, from the equation of this line, I can get k and r and replace them here. Replacing them here, I can use that as well, so I have a choice. But to get k and r, it's easier from this equation as well than from this one. So how can I get it? Is that I can take 2 points on this line and calculate the gradient, for example. So I can pause the movie and look at my working. I took 2 points A and B. A of coordinate A this one, and B this one. I look at the gradient, and remember that the gradient is log r. I use the gradient and the point to find the y-intercept log k, so I found log k. And therefore from that one I found R and K, and I found the function that the model followed by this population of bacteria. Now I can use a model to make predictions. To show you how accurate this is, I did this using a graphical software. So this graphical software gave me very similar numbers, 0 0.114, I got 0 0.116 and 2.737, 2.731, which is normal because the data is not exactly, in reality, in real life, you can't find data that follow exactly a pattern. So these are approximations. That's a way, and it's much easier to change it to a linear in order to find the equation of the population or the model. Now the question is, what kind of models can I get that need to be changed into linear? Let's take some examples. These two are the most common ones, exponential growth or decay or power law. But then there are some that are more complicated, as they look like behind them being the same ideas. So I will go into take a few examples below. In example C to E, you are required to be more creative. Let's take them one by one on the next pages. Whereas the two are very well-established models and they are generalized and you need to know, the others are just applications of the idea, and they are not things that you learn by heart. They are things that you look at and then you apply the concept in different situations. Y equals AB to the power of X. So the idea is, remember that you are given a table, you are given X and Y's, but when you graph it looks very strange. So what do you graph so that you get a linear graph? That's exponential growth or decay depending on B. If B is bigger than 1, is growth. If B is between 0 and 1, is decay, as we saw from the graphs. So I apply log in both sides. Log y equals log a b to the power of x. And I can write log y equals log a plus x log b. So I'm going to graph x against log y. So the new y on the y-axis is going to be log y. So therefore I need here a column called log y. I'm going to calculate the values and I graph this column against this column. From the linear graph, I can find the gradient and the y-intercept. Now let's look at the power rule. Y equals x to the power of n. So I apply again the logarithm because I don't want the exponents, right? So log y equals log a x to the power of n. Log y equals log a plus n log x. Now your variables are x against y. So the new y will be log y. So that's a new y. And the new x will be log x. Therefore, you are going to need to calculate log x, log y, and that's what you graph. So on the graph will be log x on the x-axis and log y on the y-axis. From the points or from the data here, you can find the y-intercept and n will be the gradient. And therefore, once you find a and n, you can go back and find the model. The models from here are extensions and are A-star material. So let's look what we do with this one. Well, I do a trick. I can't apply log because if I do log of ax plus bx squared, I can't split it into 2 to see x. So that's why what I'm going to do, I'm going to first divide by x. So I get y over x equals a plus bx. And now see how this one is the new y. And x stays as it is. So just by dividing by x and then graphing the old x against old y over old x, I'm going to get a linear graph where a is the y-intercept and b is a gradient, and I can use them to find the model here. This one is almost nothing to be done. So y equals a times 1 over x plus b. So the new y will be the same as the old y, and the new x will be 1 over x. So if I graph 1 over x against y, I'm going to get a linear graph. Now, as you got the idea, you can pause it and try this yourself. How do I transform it into a linear graph? So I'll multiply by square root of x and I get y square root of x equals ax plus b. So the new y will be x square root of x. The new x will be the same as the old x, and this is going to be the gradient and the y-intercept. Another one that you can try yourself. Probably you got already this. I multiply by x. And I get x squared y equals a plus b x squared. So the new y will be x squared y, and the new x will be x squared. This one has another solution as well. So you might have approached another method. Xy equals a over x plus bx, and you can divide by x. And then you get y equals a times 1 over x squared plus b. So the new y is old y, and the new x is 1 over x squared. This example is very similar with the previous one, and it's already done. If you think of y being a times 1 over x squared plus b. So this one is the new capital X, and the new y is the same as the old y.